Will do.
I don't know how long those spots will be open.
Yep.
All right, so what do you want to go over tonight or today?
You there?
Yeah, can you hear me?
Yeah, sorry, that was weird. It kind of cut out. Must be this weather or something.
Okay.
That was weird. Okay, so the first one is to graph each function using radians of negative 2 pi to 2 pi.
Okay.
And it just wants to identify the zeros and the asymptotes.
Mm-hmm.
So it is y equals 2 cosine theta.
Seeing this more and more, where it goes instead of 0 to 2 pi, where they put the domain from minus 2 pi to 2 pi. And
yeah.
Just want you to graph it, right?
Yeah.
Okay. What would the normal sine curve look like? Yeah. These are my toughest problems to do online. Because what I'd really prefer to do is have you graph it. Well, if I graph cosine, you definitely need to know what cosine looks like.
Yeah.
Okay? And that normally would go from 0 to 2 pi, and that would be one cycle, and it would go from 1 to minus 1. That's what y equal cosine of theta would look like from 0 to 2 pi.
Yeah.
Well, what's the consequence of the 2?
Doesn't it increase the amplitude?
Yeah, it's a vertical stretch factor. So instead of going from 1 to minus 1, it's going to go from 2 to minus 2. So if I draw that in red, it's going to go through the same quarter points. So in other words, it's going to drop down and go through the horizontal axis there. It's going to go down to its minimum there. Going to come back up through the horizontal axis there and come back up to its starting point there. Now, that's one cycle.
Mm-hmm.
If I want to go from negative 2 pi to positive 2 pi, then I got to draw the rest of it over here. And cosine being, this isn't really necessary to know, but cosine is an even function, meaning it is symmetrical with the y-axis. So all I got to do is draw this curve and reflect it over the y-axis.
Yeah. Okay.
That's not
I remember that.
quite what I meant. Just realized that I erased the wrong curve. In other words, I had a red curve here. That was y equal 2 cosine of theta. Let's erase the black curve, which is what I wanted to erase. There. Now, that's correct, except it doesn't go far enough on the domain. It needs to go there. Now you have the curve that they want. I'm a little curious. Is this the way they stated the domain? Greater than or equal to minus 2 pi, less than 2 pi?
No, not in that. They stated it as the graph the function using radians from negative 2 pi to 2 pi, so in a sense it's the same thing.
Well, okay. Yeah, the only thing I was curious about is the greater than or equal sign. Because normally when they're going from 0 to 2 pi, it looks like this. Theta is greater than or equal to 0, but less than 2 pi. So 2 pi is never an answer, but 0 is sometimes. So I was a little curious here as to whether or not they use the same notation.
Yeah. I get what you're saying.
Doesn't
No, yeah.
doesn't really matter. The only difference is if it's this, then it's an open dot there and a closed dot there.
Mm-hmm. Okay.
All right, what else?
The next one is y equals sine of 4 theta.
Now, the domain is very important here. How do they describe the domain? Same way?
Yeah, same way. Mm-hmm. All of these is the same way.
So theta is greater than minus 2 pi and less than 2 pi.
Yeah.
We'll make it look like that. Okay, what's b?
Isn't b 2 pi over,
Yes, but b is 4. B is the coefficient of
okay.
theta. Okay?
Yeah.
And now that'll let you figure out the period, because the period is 2 pi over b. So what's the period?
The period is 2 pi over 4, so the period is 1 pi over 2. Yeah, pi over 2.
Okay. So I'm graphing the sine function. There's no phase shift. There's no amplitude shift. There's no vertical shift. It's going to start right there. And it's going to end right there at pi over 2. And you have to quarter that up.
Yeah.
In other words, that's pi over 4. That's pi over 8. And that's 3 pi over 8. When I say quarter it up, you know what I mean, right?
Yeah, yeah. Yeah, put it into the section.
Yeah. So this is going to go from 1 to minus 1. And one cycle of this, in other words, I got to hit the high point at the first quarter point, got to come back through the 0 at the second quarter point, got to hit the low point at the third quarter point, come back through 0. So that is going to look like that. Only that doesn't go from minus 2 pi to 2 pi. So let's go all the way out here to 2 pi. Remember theta, which is what is supposed to go from minus 2 pi to 2 pi. Right now, all we're doing is going from 0 to pi over 2. So I need basically 4 more cycles of this. In other words, I need one that goes through that. So like that. Like that. Like that. Now I've got 4 cycles of this thing from 0 to 2 pi. Well, now just go the other way, same way. And if I quarter it up, I'm going to draw a sine curve. Like that. Keep going. Like that. Keep going. Like that. Keep going. There you go. Now, does that fit everything? Yes, the period is pi over 2, which based on this 4 is what the period should be, is pi over 2. It's just that when they said graph it from minus 2 pi to 2 pi, they're basically saying give us 8 periods of the sine function.
Okay. Okay.
In other words, there's 1, there's 2, there's 3, there's 4 to the right. If I go the other way, there's 1, there's 2, there's 3, there's 4 the other way.
Mm-hmm.
But it
Yeah.
all really comes down to finding what the period is. And then just plotting the sine function throughout the domain that they have defined.
Mm-hmm. Okay. Cool. So the next one is y equals tangent of theta minus pi over 3.
Like that?
Yeah.
Same domain.
Yeah.
Okay. If I were to graph just tangent of theta, what are these asymptotes? What's this one here? Here's what tangent of theta looks like.
Isn't it pi over 2?
Minus pi over 2 on the left, positive
Yeah.
pi over 2 on the right. So what would the period be? Because this just repeats. In other words, if I draw my next vertical asymptote at 3 pi over 2, then one more period would look like that.
So the period would just be pi.
Yes, and that's key. In other words, the natural period for sine and cosine is 2 pi, but the natural period for tangent is just pi. Okay? Now, instead of drawing that, let's figure out how to handle this phase shift. What does that do?
That changes the period?
Nope. That is a horizontal shift. Just like,
That changes the starting point.
just if I had x minus 2 squared. That would still be a parabola, it's just its vertex would be moved 2 points to the right.
Mm-hmm.
Trig's no different. They call them different things, but they're still just horizontal shifts and vertical shifts. So which way should I shift this?
It would shift to the right.
Okay. So the best way I think to handle phase shifts is to figure out where you start. Okay. Well, this tangent curve starts at minus pi over 2. So I really want to do minus pi over 2 plus pi over 3. That's where I'm going to start. Well, that's minus 3 pi over 6 plus 2 pi over 6. I'm going to
So you start at negative,
negative pi over 6 right there.
okay, yeah.
And now the period hasn't changed, so the only thing I'm doing is moving my vertical asymptote to the right by the phase shift.
Yeah, so the vertical asymptote on the right becomes 5 pi over 6, right?
Exactly. In other words, if I know my period, which is pi, then I take where my starting point is and I add pi to it, and my next asymptote is 5 pi over 6. And let's erase the black line. I don't need the black line anymore. That was tangent of theta, not tangent of theta with a phase shift.
Yeah.
And my curve is going to go like that. And the only thing is that that curve goes from minus pi over 6 to 5 pi over 6. And they want me to graph it in the domain that they have given me. So if I go back and put the full domain on there, let's see, if that was minus pi over 2, then pi is about there. I got to go all the way over to there to get, hold on. So we'll call this minus 2 pi. We'll call this plus 2 pi. And if I draw my asymptotes, a bunch of them, what's this asymptote at?
The one on the left side, it is at negative 7 pi over 6.
If I go over one more period, that's negative 13 pi over 6. Erase that because that no longer is appropriate. Okay, and now let's go to the right. That's 11 pi over 6. So 2 pi, no. I was going to say, if that erased that whole thing, I am going to be
Oh, yeah.
furious. Okay, so here's what we got. If we're trying to plot this curve, I've got one period plotted. It's just it goes from minus pi over 6 to 5 pi over 6. Okay, well, I can certainly plot one more period. And I can plot a period over here. Same shape curve, same amplitude, everything. But now, if I want to go to 2 pi minus 2 pi, I'm looking at that. So that curve would look like that. It would just be a partial curve. And if I want to go to the right of 11 pi over 6, let me erase that 2 pi that obviously is not correct. 2 pi is going to be right about there. And I would go to about there. So that's what the graph looks like given this domain.
Okay.
Notice that I have a partial tangent curve there because I'm only starting at minus 2 pi. I'm not starting at minus 13 pi over 6.
Yeah.
I have a full tangent cycle there, a full one there, a full one there, and I have the part that's missing from the first one over here.
Okay.
You see why the beginning and the end one are just partial graphs?
Yeah.
Because they don't go fully from vertical asymptote to vertical asymptote.
Okay.
Now, yeah, okay. Yeah, no, that's exactly the way we want to do that problem. All right.
Okay. The next one is y equals 3 cosecant of 2 theta.
No phase shift, so let's see what cosecant is. Cosecant sits on top of the sine. So normally cosecant would look like this. That would be one period of, this would just be y equals cosecant of theta. Okay?
Okay.
And it would go from 0 to 2 pi. Now, the 3 doesn't do much. Let's talk about the 3 secondarily. What's the 2 do?
The 2 changes the period.
To what?
It would change the period to pi.
So let's just erase the 2. Now we're looking at cosecant of 2 theta. This is our black curve. Now in red we'll add the amplitude. Because all I really have to do to add the amplitude is make that say 3 and make that say minus 3.
Yeah.
Don't really have to redraw anything. That's the secret when you're graphing trig functions or sinusoid functions. Don't label anything until you get done, and then you won't be... I constantly found myself not having a large enough page to draw it on.
Yeah.
And so the secret is just don't label it until you're done. So this curve is now that. The only thing is we haven't gone from negative 2 pi to 2 pi. So let's put 2 pi there. I still need a little more room than I gave myself. Not really, actually. So I'm going to just duplicate this thing for the other 2 periods. Notice that there are vertical asymptotes everywhere where the sine is equal to 0. Right? Because if the sine's equal to 0 and the cosecant is the reciprocal of the sine, well, you're going to have you can't divide by 0, so you put a vertical asymptote there.
Okay, so I have one question though. Why on the negative is the sine from 0 to pi, but on the positive it's from 0 to half pi, pi over 2? You see what I'm saying, the sinusoid curve?
Say your question again.
So in the positive domain, from like 0 to 2 pi, the curve goes every half pi, so there's 2 for every period, but in the negative there's only...
That's because of one thing. This 2. That 2 made our period equal to pi, not 2 pi. So we're going to do one complete cycle, which is top and bottom, every pi.
Yeah, I understand that. So in the
one complete
negative
cycle. Okay, did I label it wrong? I might have labeled it wrong. No, I think I labeled... Oh, I did label it wrong. Yeah. Sorry. Let me go back. Now I understand your question. So let's see. This is the y-axis. So I've got to have 2 cycles between 0 and pi. So it's got to look like this.
Okay, cool. That's what I was just wondering about.
No, I definitely had made a mistake on drawing it, and I didn't realize it until you said that. So there you go. And there are 1, 2, 3, 4 cycles, which there should be. Because if we're going from minus 2 pi to plus 2 pi, and the period is pi, I should have 4 complete cycles of the cosecant curve.
Okay, yeah.
All right.
Cool.
Sorry about that. That's a good pickup, actually, on your part.
Oh, no worries. I was just wondering because I didn't want to...
No, I'm glad to see it. When I make a mistake, that's the best thing that can happen, is you can pick up on it. It means you're really following it.
Okay. The next one is y equals secant of theta minus pi over 2.
I like the way they're doing this. All right. First of all, I'm going to draw just y equals secant theta. That is 3 pi over 2. That is minus pi over 2. In other words, I'm going to have vertical asymptotes wherever the cosine is 0.
Okay.
Hold on, I didn't do this right. What happened? Oh, right. No, the cosine is equal to 0 at pi over 2, and minus pi over 2, and 3 pi over 2. So I'm going to have vertical asymptotes like that.
Yeah.
Okay? The only difference in this function, the period's the same. The period is still 2 pi. But what does this minus pi over 2 do?
It changes its starting point.
Yeah, it makes this the starting point. So in red, if I shift my existing black curve to the right by pi over 2, falls there, there, there. Let's see, if we go the other side, let me think for a second. I guess it does this. I'm not sure we have a full cycle on the ends or not. Let's figure it out. And the way to figure it out is your vertical asymptotes. So what are my new vertical asymptotes?
For the right side, it would be 5 pi over 2, and then 7 pi over 2.
Well, we're already beyond 2 pi, so we don't need to go to the right of that. So go left, that's minus 3 pi over 2, and that's minus 5 pi over 2. So let's start erasing some stuff.
So it stops when it hits 5 pi over 2, right?
No, it actually stops when it hits minus 2 pi, because they wanted you to only draw the curve from minus 2 pi to plus 2 pi. So this part of the curve, half of it's missing.
Okay.
It's not like that. It's like this. And this part of the curve is completely missing, but this part of the curve, half of it's missing. So it's like that. And then let me erase all of the black. And there we have it. And that is 2 pi, and that is minus 2 pi. So we've graphed the curve, and it looks like we have 2 full cycles.
Okay.
That's 1 full cycle. That, combined with the first piece, is another full cycle. And since the normal period of secant is 2 pi, and we're going from minus 2 pi to 2 pi, we should have 2 full cycles. Exactly. No more, no less.
Okay. Yeah. Okay, I see how that works.
That's how you have to do these. And you do have to draw them partially. And, I mean, as long as they have said that that goes from minus 2 pi to 2 pi.
Okay.
Then I want my right endpoint not to be 5 pi over 2, but to be 2 pi. And my left endpoint to be minus 2 pi. So that's really, and I don't need that, and I don't need that. So I would expect if you were given like a multiple choice and they were giving you a choice of graphs to look at, this would be exactly how your graph would look.
Okay.
All right.
Cool.
What else?
The last one is y equals cotangent of theta over 4.
I like these where they're only giving you one adjustment. The ones where they give you like all 6 adjustments in one function.
Oh yeah, at once.
Well, you can do them. It's just that they don't teach you as much. You learn more by doing 1 or 2 at a time.
Well, I can figure out what I'm doing at a time, which is nice.
Yeah, well, if I was graphing just cotangent of theta, it would go from 0 to pi, like that. That'd be one cycle.
Yeah.
So, what's the period here? What's B, first of all?
B is 1/4.
So what's the period?
Pi over 1/4. So it would be 4 pi.
So rather than redraw my curve, let me just label that 4 pi. And that's what I meant by don't label your x-axis until you figure out what your period is. That's correct. It just, they only wanted to go from, in other words, if I were to draw one more period in the places where they want us to draw it, well, this is clearly minus 4 pi. And since they only want us to go from minus 2 pi to plus 2 pi, this function is going to look like, it's going to look weird. In red, and I don't even have the entire next part of it.
Yeah, okay.
There you go. That's from minus 2 pi to 2 pi. Now that doesn't look like a tangent curve, but that's because we're going from minus 2 pi to 2 pi. If we were going from minus 4 pi to 4 pi, we'd see 2 cycles, 2 full cycles of the cotangent curve. What we're really seeing
I see.
a half a cycle there, and we're seeing the other half cycle there. In other words, since they restricted us to minus 2 pi to plus 2 pi, we can't go to the left of that black line or to the right of it.
Yeah, I see.
All right? What else you got, Nick? God, I'm glad they're not vectors.
Yeah, you're telling me. No, thank you.
Well, I'm glad I'm not the only one that has a problem with vectors.
They're just kind of confusing to me.
They're very tough. They're very tough. Unfortunately, they're very important. In other words, in the real world, 3-dimensional vectors are, that's everything. You know, an airplane is actually flying 3-dimensionally, not 2-dimensionally.
I bet my dad might know about that a lot because he's a pilot.
Yes, he definitely would. There's no way you're becoming a pilot without taking a course on 3-dimensional vectors. Because the other thing is that planes have velocity, which is a vector. Velocity is a vector. It has magnitude, it has direction. Same thing as a force. So anything involving forces or velocity of things in the real world basically involve 3-dimensional vectors. So it's a hard subject to avoid if you want to go that far in math. And not that hard. I don't know why I have such a problem with it. It's probably just I don't get enough chance to do it with students. I get very few students that do three-dimensional vectors. I get, well, like one every 3 years. Seriously. And so by 3 years, I've forgotten what I learned 3 years prior, and I never do get refreshed.
Yeah.
Like I said, send me a note if it's a really tough subject, and I'll try to refresh before we have a session. But anyway, what do you got next?
The next thing I have is to find the exact value of each expression.
Okay.
And it is cosine of arctangent of 3/4.
These are the easy ones. By that I mean you have the trig function on the front and you have the inverse trig function in the middle. When you get those, these are really easy. Just make sure you follow a certain methodology. That is an angle. Okay?
Okay.
It's important to realize that. You take inverse trig functions of ratios to get angles. So that's some angle theta. So we're really saying, what's the cosine of theta? Now, when you can bring it down to that, draw your triangle, label theta. What part of that triangle can you dimension?
The opposite and the adjacent side.
Which makes that 5. You can use the Pythagorean theorem to calculate that. And now what's the cosine of theta?
The cosine is 4/5.
That's the easy way to do it.
Okay.
That's all you have to do. And notice one thing, very important here. We never solved for theta. You could have done this the hard way, which would be enter that into your calculator, and it's going to give you an angle of like 37 degrees. And then take the cosine of 37 degrees, and you're going to get 4/5.
Okay.
That way requires you to figure out what theta is. Well, not only does it give you an approximate answer, but there's no need to figure out what theta is. As opposed to if I had the inverse cosine of tangent of pi/3, something like that. Notice in this problem, that's on the outside, that's on the inside. I can no longer say that's theta. And so the only way I can solve the lower problem is to figure out what the tangent of theta is, which is over square root of 3. So now the problem becomes what's the inverse of 1/√3. And I can solve that also, but it requires you, this kind of problem requires you to work from the inside out. And this kind of problem you could also work from the inside out, but you don't need to. This is really the easier way to do it if the inside is an inverse trig function.
Yeah. Okay. The next one, and this is actually the last thing, it wants us to write an algebraic expression that is equivalent to the expression.
Okay.
And the expression is tan of arc cosine x/3.
What am I going to do as a first step here?
Sorry?
What do I do as the first step?
Draw your triangle.
Well, okay, yeah, I'm going to draw a triangle for sure, but I'd say the more important first step is to recognize that that's an angle and label it such. because you
Okay.
have to label theta on this triangle. And I got two choices. I can put theta at the top or I can put theta here at the lower right. Well, I traditionally put it down there, but it matters because where you put it is going to determine how you dimension the triangle. Now, dimension that triangle as much as you can.
The adjacent side would be x, and the hypotenuse would be 3.
Making the opposite side?
Making the opposite side square root of 9 minus x squared.
Now, what's the tangent of theta?
Equals root 9 minus x squared over x. And that's it?
Yep. And notice here, we really couldn't figure out theta even if we wanted to. But we didn't need to. In other words, is all I needed to know was that that was some angle theta, and that allows me, knowing that the inverse cosine of x over 3 allows me to dimension two sides of that triangle, which means you can always dimension all three sides, and then you can take any trig function you want of theta.
Okay.
Just in terms of variables instead of in terms of numbers.
Okay, cool. Oh, that makes sense. Well, that was the last thing I had, actually.
Okay. Yeah, we can stop here. I'll just charge you for 3/4 of an hour, and we'll touch base again Sunday night.
Awesome. Thank you very much, Ms. Cohen.
You're welcome. Talk to you later.
Talk to you later. Bye-bye.
Bye-bye now.